Let's talk about exponential graphs and how we use them to compute limits. So you can see here, I've started with the two main types of exponential graphs. So a basic exponential function is just y equals some number to the x power, where that number is anything greater than 0, but not exactly 1, because any power of 1 would just be 1. Right. So we have this positive base, and it's going to fall into one of two categories. It's either a number greater than 1, or it's a fraction between 0 and 1. Sometimes they show up as decimals, but typically fractions. So if the base of the exponential function is greater than 1, so we're talking 2 to the x, 3 to the x, 10 to the x, etc., the graph will look like this that you see here. So it is increasing from left to right. It has a horizontal asymptote at y equals 0 on the left end only. And it will have a y-intercept at 1 because any number to the 0 is a 1. That's not to say that every one of these graphs is identical. They have roughly the same shape, but if you graphed them on the same xy plane, they would look different. For example, 2 to the x and then 3 to the x would be steeper than it, but they would still have these general features. And typically when we're computing limits like we're going to do below, this amount of information is plenty to get by with what we need. Right, so the other type of exponential graph is if the base of the exponential is a number between 0 and 1. So this would be something like 1/3 to the x, 2/5 to the x. Sometimes you see it as a decimal, so like 0.7 or 0.9 to the x, anything less than 1. In that case, higher powers of that number actually don't get bigger, they get smaller. So what we have is sort of a reflection of the original graph over the y-axis. So it's decreasing from left to right. It has a horizontal asymptote at y equals 0 on the right end only, but we still have that same y-intercept at 1 because anything to the 0 power is 1. And again, the individual graphs are slightly different from each other, but knowing this general shape will be enough to get by for all the limits below. Okay, let's try a few. So I have some limits prepared to talk about. The first one here is the limit as x approaches infinity of 10 to the x power. So I look at this 10 to the x, and I think, okay, that 10 is greater than 1. So this graph roughly looks like this here. So if x is approaching infinity, I'm talking about the far right end of the graph, which is pointing upwards. So it just goes up, up, up forever. So this limit doesn't exist, and specifically it equals infinity. The next limit uses the same function, but it's the limit as x approaches negative infinity. So I'm still thinking about the 10 to the x graph being one of these increasing ones. As x approaches negative infinity means the far left end of the graph. And this is the part that's kind of asymptoting out towards 0. So this limit is 0. Let's try a few more. So you can see here we have the same two limits, x approaching positive and then negative infinity. But now with our function is 1/3 to the x. So here the base of the exponential 1/3 is less than 1. So 1/3 to the x is one of these guys. So as x approaches positive infinity, we're headed towards 0. So this first limit is 0. And then as x approaches negative infinity, that's the far left end of the graph, and this is going up, up, up in y values. So this limit is positive infinity. We can also use our knowledge of these basic exponential graphs, just number to an exponent, to do slightly weirder limits, which is what I have coming up in the next few examples here. Okay, so for example, 14 over e to the x. You do have the option to reformat this as an exponential 14, 1 over e to the x. And then you could categorize it as the second decreasing type and answer it that way. Or you could think of it exactly as it is and just say, all right, on top, I have a fixed number, 14. And on the bottom, I know e to the x. E is about 2.7-ish. So it's one of these pictures. So as x approaches infinity, it just gets bigger, bigger, bigger. So I have a number over something going to infinity. So that limit will be 0. Either way you think about it, this should be your final conclusion. All right, let's try the next one. This one's a little bit different. All right, so here our function is 3 to the 1 over x plus 4 to the negative x. 3 to the 1 over x technically isn't a normal exponential, but we can still kind of get by to a final answer here. All right, so first thing is to consider 3 to the 1 over x separately. And I say, all right, well, this is not the setup that we've been talking about. This isn't just 3 to the x, so I don't really know what this graph looks like. So I'll zoom in kind of to the smaller pieces and see if I can kind of pick it apart that way. So if I look just at the 1 over x part, I say, well, I know as x approaches infinity, 1 over x, much like this, is going to go to 0. So that limit, that 3 to the 1 over x part is going to go to 3 to the 0. Okay. And then over here, again, we have two different options. They both come to the same conclusion. You can kind of decide between the two. So one option is to leave the formula exactly how it is here, 4 to the negative x. And think, okay, this doesn't exactly fit the two function types above, but I can think about it in pieces. So as x gets very, very large, this exponent is a negative large exponent. So we have like 4 to a negative big number. And we know that that is really 1 over 4 to a large number. So it's really going to be one of these where the bottom is getting bigger and bigger and bigger, and it goes to 0. So this limit right here will be 0. If that thinking doesn't quite sit right with you, another way to think about it is to reformat it as one of our exponentials. So 4 to the negative x is 4 to the negative 1 to the x. So I can see this as like just plain number to the x, so it fits my graphs. 4 to the negative 1 is 1/4 to the x. So I say, oh, okay, the far right end of a 4th to the x would be one of these guys headed towards 0. And that's probably a smoother way to decide it heads to 0. Okay, so altogether, we decided it was 3 to the 0 plus limit 0. So overall, our limit is 1. This next limit here is the most involved one. It's kind of a combination of a bunch of the stuff we were just talking about. All right, so as x approaches positive infinity, here I have 2 times 0.9 to the x. So we could think about 0.9 to the x as its own exponential, which would have the decreasing exponential graph type. Or we could consider the 2 with it as well. Times 2, this graph is not going to change the fact that this limit is 0. Right? So as x approaches infinity, 0.9 to the x is headed towards 0. So why don't we say this part of it goes to 0. Over here, again, 4 to the 1 over x doesn't quite fit our exponential structure. But just like in the last example, we know the 1 over x part goes to 0. So in the next step, I'll make this 3 times 4 to the 0, which will be 3 times 1. Very similarly, on the bottom, 1 over x squared, the exponent on the 2, goes to 0. And I'm going to plug all these zeros into their spots to keep it organized. So this will be 2 times something we said goes to 0, plus 3 times 4 to the 0 power, over 5 times 2 to the 0. And I'm going to very carefully compute here. 2 times 0 is 0. 4 to the 0 is 1. So this is 3 times 1, or just 3. Same thing down here. 2 to the 0 is 1. So this is 5 times 1. So this limit is 3 over 5. The last limit I want to talk about in this video, you can see here, x is approaching negative infinity, and our function is -4 2/5 to the x. So there's two different ways you could think about it. If you want, you could just highlight this 2/5 to the x part and say, okay, you are a fraction to the x, so I know your graph looks like this. So as x approaches negative infinity, we're going up, up, up to infinity. So I know this part is approaching positive infinity because the graph is going up. If it's times a -4, now we're actually switching to negative large numbers. So this limit is negative infinity overall. So I said there was two different ways to think about it. That's one of them. The other way is to think about the function y equals -4 2/5 to the x altogether. So not just highlighting 2/5 to the x and bringing it back here, but thinking about this whole thing as one function. What this -4 would do to this basic graph shape, the 4 is going to stretch it a bit, but it kind of keeps the same shape. The negative is the important part. So having a times a negative on your function flips it upside down this way. So this graph, roughly, instead of being the regular 2/5 to the x, is going to be kind of upside down like this because of the negative sign out front here. So as x approaches -infinity, we're kind of coming down the far left end of this graph, and you can see it going down, down, down. So that would also bring us to the same conclusion that the limit is -infinity.